So what we need here is whether the second row is an event or not, 8th row is an event or not, or 12th row is an event or not from the training set. Because for the first validate observation, row 2 is the k equal to 1 closest observation, row equal to 8 is the second closest, and row equal to 12 is the third closest. So I'm going to use an if to convert the ownership to 1 and non-ownership to 0. So we start with an if, and then we do an offset. Now offset starts from a particular cell. Suppose if that's the cell that you want to start out with, so that will be G7, and you always start counting from there, and how many cells down we want to go, how many cells across we want to go. So across for ownership is 1, 2, 3. Okay, that's 3. How many cells down is, okay, if it is the same row like G7, then you don't go down at all. Okay. If it is for row 2, you have to go down 1. If it is row 3, you have to go down twice. So the number of rows you want to go down, so G7, comma, right, you need to go B64 minus 1, because second row would be if you go down just once. So it should be B64 minus 1, comma 3. That will give you the offset. Okay, whether that will give us the value of the event, owner or non-owner. Okay. Then if it is owner, so if this should be compared to owner. If it is owner, then I'm going to put 1, otherwise I'm going to put a 0. Okay. Put that down and across. Okay. Now the propensity is the average of these. So that will give you propensity for the event. Okay. So approximately, I think 6. All right. So let's go up to 6. It should be 1 after that. All right. So prediction then is if it is greater than the cutoff point, you would predict owner, so cutoff point of 50%. So if the propensity is greater than or equal to the cutoff, okay, then you predict owner, otherwise you predict non-owner. So that's your prediction. So now the question is whether that prediction coincides with, we know from the validation set whether that was an owner or not. So validation set, first observation, okay, is owner predicted as non-owner. Second observation, owner predicted as non-owner, and so on. So we can figure out whether we have true positive or false positive true negative or false negative. So that would be if, okay, if B74 is equal to owner, okay, and if, so if it is owner, and also if B40 is owner, cases may have to, you have to keep track of cases. So in that case, if both are owner, then we have a true positive. Okay. Otherwise, we have zero. That's not true positive. Okay. So there are two ifs. You have to make sure that it works properly. The false positive would be if you predict positive, okay, but the actual is non-positive. So that will be like if B74 is owner, okay, you predict as owner, and if B40 is non-owner, you predict owner but actual is non-owner. So that would be false positive. So false positive will be a 1 then. True negative will be if our prediction is non-owner and if the actual is also non-owner. The actual if P74 is non-owner, comma, B40 is also non-owner, okay. Here I should have an if B40 is non-owner. Okay. So then we have a true negative, otherwise not. So that will be true negative. False negative will be if we predict non-owner and if the actual is owner, then that would be a false positive, false negative, sorry, false negative. Copy this across. So each validation observation is now classified either as one of those four. Is it a true positive? Is it a false positive? Is it a true negative or is it a false negative? So each observation, each validation observation is classified into one of these four groups. Now when you sum, you get the total for k equal to 3. Okay. So that's your true positive. True positive is that. Okay. False positive is that. This will be true negative and false negative. Here is our confusion matrix for k equal to 3. So now we can build the measures. So accuracy is what? That plus that divided by that would be the accuracy rate. Yeah.
Non-order 64 switch.
So that should be that. Thank you. Alright, so accuracy error rate would be 1 minus that. Okay. Sensitivity is going this way. So actual of all the owners, how many are correctly predicted as owner? That would be sensitivity. Specificity would be of all the non-owners, how many are predicted as non-owners? Okay. False positive rate is among those who are predicted as positive, how many are non-positive? So it will be that. And false negative rate is among those who are predicted as negative. Okay, how many are positive? Okay, so these are the accuracy rates. Yeah. Now we can do this for different case and compare. So the key here is to separate the training and validation set. That's one of the problems with k-nearest neighbor, because in other methods you don't have to have a validate set to be able to compare the models. We do it because that's a good idea, okay? Not because we have to. So here, without separating into a validation set, there is no way to compare different cases. And therefore, in the choice of our modeling itself, the modeling itself requires your validation set. And therefore, in order to verify whether the selected model is good, you need a third data set to test it out. So that's the reason why we have test data set. Most situations we don't need test data set. We only need train and validation. Right? Here is a case where, because validation set itself is used in modeling process, okay, we need a third data set for verification. So that's the reason why in SAS Enterprise Miner in partition node, you will find there are 3 things given there: train, validate, and test. Okay. So here KNN is a situation where test data set is useful.